here. Thanks for joining again for the next HCPS Desmos PL opportunity. Today I'm going to be leading a session on using movable points, just how to create them. No computation layer used at all, although you certainly can use computation layer later on once you know the mechanics of how to create movable points using sliders. So I'm going to get myself out of the way here and invite you to join this class code. So if you go to student.desmos.com, and then you can join with UBUZF6. I'll leave that open and just show you what it is that we're taking a look at. I'm trying to move myself in this corner. I have just a series of screens, wondering if you think you know how to create this screen. And I'm referring to things on the left here. So we see a graph with just a drag me point that when I drag follows me wherever I go. That's going to be, at the most basic, what we learned to do today, how to create a draggable point. Then I've changed some things. So on this screen, as we drag it, I'm tracking the coordinates with integers. Here I'm asking you to complete a linear pattern. Again, it looks like it's snapping, but it's not telling me where I am. Create a number line. Place these points on a number line. You'll notice they can go as high up as where they started and as far down as the number line. Can you make two movable points that will always create a line no matter where I drag them? Can you trace a hidden function? This one is a really fun one. What's the hidden function? Drag the point to explore. Wonder what's going on there. And then something like tracking an increasing interval. So let me scoot down here. As I drag this point along the x-axis, I'm noticing this little green one tracing my function, and this is tracing the height, f of x, at that moment. It's kind of a lot going on there, but it's all reliant on this draggable point. And then the last one to explore is, well, if students can't access sliders, maybe we can give them control of sliders so that they feel like they are changing the y-intercept and changing the slope. So those are things that we're going to look at today. I'm going to start by just trying to recreate this draggable point in the Desmos graphing calculator. So right here, to get a draggable point, all we are going to do is add any point, a comma b, for instance, and then hit slider, add all. Now I've created a point. It's got two variables, a and b, as my x and y coordinates, and now I can move it around. That's the simplest way to make a draggable point in Desmos. Now, if you recall, over here we had drag me as a label, and it followed everywhere. So the way that I added that, when we look at our points, I click label and I wrote drag me. Now that label is attached to this point no matter where it ends up. And just like that, we've successfully created a draggable point and labeled it drag me. For slide 2, I added something here. I added another integer label, and the drag me disappears. And I'm also keying in on the fact that I'm attaching to the lattice points only at integers. So let's kind of start with this drag me. I'm going to go and clear this and pretend like we're starting from scratch. So again, I've got A, B, and all. I did have a label, but this time I wanted the label to be integers just like this. This is great. But I want to snap to integers. And the way to control that is to actually go into the variables themselves and make them a step of 1. So I just click here on right beneath the slider in the range where it is. I click on either the low or the high end of that range. I change the step to 1. Now when I interact with my point, it will snap to integer coordinates, which can be helpful if we're asking students to place something in a specific integer. Now I've got the ordered pair showing up, but I had a drag me. Remember right here, I had this drag me that started. So I wanted to signal students what I needed to do. And this is a little bit sneaky. In order to get the drag me to show up, I actually need to add a second point. So I'm going to add a point here, and it's also going to be a comma b. I have a new point, and I'm going to label this one drag me. I want it to blend in, so I'm going to make it red, so it's the same as what I had before. Now the problem is, as I move, this drag me comes with me. And so what we're going to do is add a restriction. I'm going to go ahead and get rid of, well, I can leave that there. I'm going to add a restriction here that says, hey, I only want this to show up if A equals 0 and if B equals 0. And now when I drag the point, you'll notice that now that A and B are no longer 0, that point has disappeared. But when I come back to 0, 0 at the origin, the drag me message shows up again. So that's one way that we could do that. You could have named this any point. Since I wanted it at the origin, it could have been 0, 0, and it only shows up when A equals 0 and B equals 0. It's the same effect. It's really this restriction that is making us believe that the drag me point is attached to AB, but it's the restriction when A is 0 and B is 0. So now you know how to add a label, how to change the steps for where coordinates can end up, and then how to use a second point relying on our first one to place points. With that, we can start to do a lot more interesting things. Now that we know how to create a movable point with a label, we can give students a target, right? I want you to complete this linear pattern. So my message is no longer drag me, it's complete the linear pattern. Well, let's take a look at what we've got going on here. I've got 3 fixed points at, it looks like 0, 3, at 2, 2, and at 6, 0. So I'm going to go back to my screen here. I'm going to delete everything. And we have lots of options for how we can enter those points. I could enter them as a list of ordered pairs separated by commas, so 6, 0. I could absolutely do that. I also could have added them as a table. So I'm going to go ahead and click this and convert it to a table. I could have done this. And for various reasons, I think it looks a little nicer. It's easier to read, but it's not wrong to leave it as it was, as 3 different points. But if I had like 10 points, a table is just going to be a little bit more flexible for me. And I can use this magnifier to zoom in if I'd like. I do not want to, so I'll zoom back out. The next thing that we had, if I look back at our screen over here, I needed to complete the linear pattern with this movable point. So I'm going to create a point. Again, I'm just going to use AB. I could use anything I feel like as a slider variable other than X by itself, Y by itself. E is reserved as a number. Most letters will work. You'll get an error message that it won't let you add a slider if it's unavailable. I wanted this to start at -5, -5. So instead of moving the slider, I can set the value in and manually changing them. So -5, -5. I want to add a label, right? Complete the linear pattern. But again, I only want that label to show up at -5, -5 when A is -5 and B is -5. So I'm going to go ahead and take this label. I'll make a new point. I'll do it at -5, -5. I only want that when A equals -5, B equals -5. I'm actually going to take this label from my draggable point and put it on -5, -5. Complete the linear pattern. I'll make this blue to match my label there. And now I've got this nice interaction. -5, -5. I start to move my point. Now you'll notice I'm freeform. Let's go back here and take a look at our activity. I believe it snapped to integer coordinates. It did. So all I need to do is change my A and B steps to match that. So I'll go back into the screen here. A can step by 1. B should also step by 1. And now I've got this snapping to integers. And the reason I want to do that is I want a student to place this exactly right, precisely. I don't want them to be super, super close and feel frustrated when it's marked wrong because they're at 4.02, comma 1.1, right? We want this to just snap. It's a linear pattern. As long as they get to this lattice point, they'll be correct. A really popular thing to do with movable points is to create a number line. And we can do that by actually altering the grid itself. And then we can add several points with labels that follow the point. And we can ask students to place things on a number line. So let's take a look at how we do this. So I'm going to reset everything. And we came to Desmos.com. We've got this nice calculator. And I actually want to get rid of the grid because I just need a number line. So I'll do projector mode so you can see this a little bit better. Sorry, I didn't have that on earlier. I'm going to turn off the grid, and I no longer need my y-axis because my number line is going along x. Now you'll notice I don't have enough spaces here in between 0 and 5. I don't have those hash marks. that let me know where I am. I'm going to make this by step of 1. And let's see if I change this to maybe negative 9.5, that might do better. There we go, negative 9 to 9. Desmos doesn't like it when you get too wide. I'm not sure the reasoning there. It will override your steps though for larger ones. So here I've got perfect from negative 9 to 9, my number line. Let's take a look back at this original problem here. Looks like we zoomed in to get from about negative 3 to 3. I'll do negative 2.75 to 2.75. And we have 4 movable points. Okay, I'll match what we had, negative 2.75 to 2.75, and we were actually going by steps of 0.5, it looked like to me. Let's check in. That's looking good. Okay, we'll figure out how we make 17 ninths and negative square root of 5 and negative pi over 4. First thing is we need a movable point. You guessed it, A, B. Add all my sliders. All right, I've got my movable points. Now I'm going to label this, and it was negative pi over 4. If you type a different cell, negative pi over 4, Desmos gives you this nice and pretty. I'm going to copy it and paste it in there. And you'll notice that Desmos did this nice math. It changed it into a math-friendly font, but it displays really ugly over here. What you need to do is wrap this in backticks. That's right above the tab key where the tilde is. If I put a backtick at the front and the end, now I changed it back into what I wanted, negative pi over 4. I'm going to make sure that this always stays above my point. Since I've got several points coming, I want to label it above. So let's take a look at what this interaction is starting to look like. Okay, well, I can move this point wherever I feel like, and I am not exactly on the number line. So let me change some things up. I'm going to default these back to 1 and 1. I know that I want to be on the number line, which means I would be at y equals 0. And to start somewhere up above, I'm going to arbitrarily choose 2. And I'm going to go by steps of 2. Let's take a look at what that just did. I'm either going to be up at 2 or down at 0. So I'm going to try to move up. I cannot. I'm going to try to move down. And the farthest I can get is the number line. And this creates that snapping effect. So I had my point start up in space up here, and I want to attach it to a number line somewhere. So down here. Okay, I know that negative pi over 4 is roughly negative 3/4. I want this to be fluid. I don't want to control anything about the step because I want my students to place this like they would on a clothesline number line. So I know that this is a pretty good estimation. I'm comfortable with that. Well, when I start it for students, I don't want to give it away. So I'm going to put this up at negative 1, 2, and then I'm going to start adding my other points. So there's no difference now. I just have 3 more points. So let's get to it. Negative square root of 5. I'm going to do the same thing here with a new point. I can't use A and B. I'm going to use C and D. Add them in. I remember that for my y coordinate, I want to go from 0 to 2 by steps of 2. I want to add a label. And then this time I want my label to be negative square root of 5. I type it in an open cell, copy it, paste it, and once again I wrap it in backticks. And backtick at the front, now I've got negative square root of 5. I can place it on the number line, I can slide it over, I make sure I can get over to negative 2. There we go. I want to place it for students to start at 0, 2, so that they have somewhere to go. I could, if I wanted to, make negative pi over 4 start somewhere in the positive side of the number line. Okay. Oh, and I forgot to make my label above. So I hit the wrench, I keep it above. There it is. You would create the last 2 points the exact same way. I'm not going to take the time to do that here on the screen. I'll let you kind of play around with that. But you can't use E. Like I said, E is not a variable. E is for the number E. So for this one, you might consider using G. So if an option doesn't show up to add a slider, you've either used it already or it's a number. And to show you that Desmos knows that E is a number, E is 2.71828182846. There we go. All right, let's take a look at, well, now that we know how to add one draggable point and multiple draggable points, let's make them interact. So I've got 2 draggable points that are creating a line. So I'm going to start this by eliminating everything as we've been doing. I'm going to add 2 points, A, B, and I'm going to use, actually, for this, let's be let's use some more math notation here. I'm going to use h comma, add all those, and then I'm going to use x1 comma y1. Add those. All right, you'll notice that the points are on top of each other. I'm going to move them just for the sake of seeing very clearly that we have 2 points. All right, the next thing I need to do is make a line out of these points. So I'm going to go to the end of my expression list here, and then I'm going to write this in point slope format. So I know that this is going to be y equals, I'm going to just use m for my slope, and then x minus h plus k. But m isn't really what we're doing. We need to figure out the slope between these 2 points. Now, I can choose to add a slider, or I can rewrite it in the formula here. I'll rewrite it in the formula. So I just deleted m. So far I've got this. This is good. I've got a line that's always going to go through hk, but it's got a slope of 1. I need to get it so that it has a slope relative to this line. And all I'm going to do is come in here, write a fraction, to signal, well, what's my change in y? Well, my change in y is going to be k minus y1. And then my change in x is going to be h minus x1. Now, this is always going to be, in that abstract, the slope between these 2 points. So as I move around, I've got my slope. If I move this other point, it's always going to talk about those 2 points. What's the slope between them right here? And we're going to reference hk as our point that we need to go through. There you have it. No matter where I move these points, I'll always have a line between them. And then if I want to make it pretty and make everything blue, I just long click to pull up the colors. They're in blue. And now we've got a line between 2 points. There's lots you can do with this. Obviously, we're just showing the mechanics of it, but we can start to ask questions like, can you make me a line with a slope of 1/4 whose y-intercept is -3/2? Well, that's something we can ask students to do, and maybe they'll put a point at where they think -3/2 is. Maybe we can make this snap to it, and then we can see, well, do you know what would happen with 1/4? Are you going to go up 1 and over 4 like this as an estimation? I mean, what are we doing here? How can we? Anyway, that's the challenge we can start to ask once we know how to use these movable points. I mentioned this early on in the video. This is one of my favorites. What's the hidden function? Drag the point to explore. So we've got a movable point, and it's obviously following something. This is a sine wave. I know it's a sine wave because I wrote it. Maybe you can investigate and figure out 0, 1, 0, -1, 0, and that looks like it's roughly 2 pi. So there's things we could do to try to figure that out. But as a giveaway, it's sine of x. So let's hop into the graphing calculator here, delete everything. And I'm just going to write, f of x equals sine of x. There's a function. That's what we're tracing. And then I'm going to name this coordinate. I'm going to name it, though, instead of 2 sliders, I'm going to use this function to force this to be a, and then f of a. I want to evaluate a using this function, right? So I can kind of combine function notation. So now we see I've got this draggable point. You'll notice it only goes left and right. It doesn't actually go up and down at all. If I try to go up, it stays relatively still. That's because, as we know, this f of a is entirely dependent on a. So wherever you move me, I'm going to follow you. So I move left, right. Oops. I move left, right. And the point comes with me, but it follows my sine graph. This is great. So I've got my interaction. It's exactly what I want, except I want to hide it. Well, the way to hide things in Desmos is you just click the circle on the left off to the side. You can no longer see the function, but I'm still calling the function into my interaction. So now I'm tracing this function. I like to use function notation. You could do this without function notation. You could say a sine of a. That'll work as well. But I like to use function notation because what if this was something gnarly like x cubed plus 4x squared? Well, now instead of having to write a cubed plus 4a, I can just use function notation. So it saves time on a more complex example. Whoa, that is a weird looking. There we go. Slider. I don't think I'd ever figure that one out without seeing it. But now we can see how it's tracing this polynomial. I added one thing, which was a little note that said, what's the hidden function? Drag the point to explore. And I did that by creating a point. So I'll make this one at 0, 7, 6, I guess. And then I just labeled this. I said, what's the function? And then I added another one at 0, 5. Label it, drag the point to explore. And then I got rid of. Well, it looks like they're right on top of each other. Let me see if I zoom in. That helps. There we go. What's the function? Drag the point to explore. Now I can put this message for my students so that they can start dragging. I'm going to make this. But as they drag, they get that nice interaction there. And then, of course, I just change the colors so that these would match. I'll make this long click. I'll make it black. What's the function? Drag the point to explore. Here we go. This is the same idea. I'm going to track my function. So that solid green dot, it's not the draggable one, but it's going to be fixed onto whatever my curve is. And then I'm going to use a slider that's dependent on the same variable, and I'm going to force it to stay, just like we did on the number line, on 0, right, for the y coordinate. So let's take a look at how this is working at the mechanics of just these two. And then this is an extra bonus challenge for you to figure out on your own. All right, so I'm going to delete everything. I'm going to just trace, I'm going to do sine of x again. That's my trace. No, I'll do x cubed. 2 plus 4x. No, okay, maybe I did a third. Let's see if I do a third. No, I didn't like that. Okay, let's leave it as this. X cubed plus 4x squared. Lots of movement going on there. Okay, I'm going to trace this with a f of a. And I'm also going to do a comma 0. All right, I'm going to drag this, and you'll see that I'm actually forcing the blue one to move at the same time. Because I don't want students to be confused that they could drag this one, I'm going to turn off the drag feature. The way you can do that is just click on anything that is draggable and then turn off the drag. So now I've got this blue dot tracing my function. I'll move this so we can see a little better. Tracing my function based off of the purple slider's interaction. I'll make the purple slider blue. And then the one thing I want to do is label this. I want to tell you where you are. And the way I'm going to do that is x equals, and then I want to reference a. Just like in a spreadsheet, if you use a money sign and then this bracket, this curly bracket, we can start to display what that value is. It's like a constant holder. So I want you to display whatever the variable is as a string, right? I want you to take this and then display it as text. If I want that to look a little math friendly, I can wrap that in backticks. It just cleans it up a little bit. And then I'm going to force this to always be below so that it's below my number line as I drag. And now here I can see x equals whatever it is that x equals. And we've got what we wanted. I could display to students what this point, where it is. It's right up there. You can kind of determine what it is that you want to do at that moment, adding a label there. But I just wanted them to see that x controls our output, where we are on this function. And then I used the interval tracker. Did something else kind of sneaky. I said it would be like an extra challenge for you, but thinking about if this is at A0, I want this other point to be going up and down. So it's going to be wherever I want it to be at 8 and then f of a. And now all of a sudden we can track the blue point going vertically and horizontally, all by referencing one slider that a student is interacting with. Okay, one last interaction to show here, and I think it's pretty cool, is we can start to manipulate things so that students can feel like what they are moving is controlling the line. So we're going to add in a lot of what we've learned today. We're going to create 2 movable points, I should say 2 draggable points, a third point that tracks the y-intercept movement, so similar to what we just did. And then we're going to just add in this line so that students can feel like they're moving it up a switchboard essentially, but we're gaming that. It's a shell game. We're forcing it to end there, and then you'll notice that I'm actually changing the equation. So that's something another extra bonus that we'll take a look at here. So and then slope, of course, control slope. So we've got a lot going on here. Let's dive in. So I'm going to start off. By writing the equation of a line, y equals mx plus b, and I'm going to add my sliders. Okay, now here we've got slope and y-intercept. I can control them with a slider here, but we want students to be able to control them with sliders on their screen. So I'm going to add a movable point that is, let's see, at negative, I'll put them at -4, -3. That's where I'll put my points. So when x is -4, I'll control the y-intercept. So I do -4 comma b. And then at -3m, this is going to be what controls my slope. So let's take a look. I'll label this y-intercept. Oops, y over to the left. And then I will add a label here that says slope, and I'll put that over to the right. So now we know exactly what we're talking about. Okay, I can move this up and down. You can see Desmos is letting me know these are going to be vertical sliders, and I'm moving this line. Now, for math teachers, we know that we're changing the y-intercept. We know to focus in here. But I think some students don't really realize, they might think that the line is kind of moving diagonally, right? As I go up, it's kind of coming up and to the left. It's a little bit hard to see. I want to make it very explicit that what we're doing is changing the y-intercept, this point. So I'm going to add one more point at 0 comma b. And I'm going to turn off the drag feature. I just want that to live there. I'm going to make it purple so that they see it's connected to my y-intercept. As I move up, as I move up, my line is coming up, and now I've kind of really forced students to see that this is the direction that I'm moving. The purple isn't coming any closer to me, it's going up and down the y-axis. I'm going to go ahead and change the step, and I'm going to force a line to happen so that it looks like we can only go from, I think I went from half to 3. Let's check back here. I went from half up to 3. So we'll recreate this exact interaction. Since I'm at -4, I'm going to say, well, let me get myself a line here. X equals -4. So now I'm on a line. But I'm going to cut this line. I'm going to restrict it from 0.5 is less than or equal to y is less than or equal to 4. So now I've got my switch running from half to 4. I'm going to change my step to go from 0.5 to 4 by steps of 0.5. Now I've got this jumping idea similar to what I had before. Okay, I like that. We're going to do the exact same thing with slope. So I'm going to come in under slope, and I'm going to say, hey, let's make a line, x equals -3. We're going to go from 0.5 up to 4, excuse me, by steps of, that doesn't matter. Oh, I'm so sorry. Scratch that. X equals -4, I apologize. We need to add a restriction here from 0.5 less than or equal to y. I'll make it so that my slope, so I need to go up to m. Here's where I need, from 0.5 to 4. Now I've got this nice interaction where I can't go any lower or higher than the tops of, or the endpoints of my line segment, and that's because I'm forcing this slider to go from 0.5 to 4, no higher, no lower. And then I've also matched that with my line segment, 0.5 to 4, that's my range. So now it looks like I can make this switch happen, this y-intercept happen, this is great, but I want students to see what that equation looks like. And now we're gonna add in a dummy point with a label. And it's gonna be a dynamic label. So this time I'm gonna go, I'll make it at -4 comma 6. So I'll do it way up there. And I'm gonna label this, and I'm gonna write y equals mx plus b. I'm gonna wrap it in backticks for math font. I'm gonna hide the point. So we've got our equation up here. Well, I don't want it to say m, I want it to say our specific m. So I'm gonna go money sign, curly bracket, then a curly bracket around the M. There we go, 0.5. And then same thing with B. I'm going to go money sign, curly bracket, B, curly bracket. Now I've got it displaying like I want it to. We're on projector mode, so we can see as I change the y-intercept, what's changing in the equation? The y-intercept, of course, B. Great. What happens when I change the slope? The coefficient of x gets larger. As I move up, it gets smaller. As I move down, I can see the steepness of that line changing. Hopefully, we're getting students to key in on the constant is referencing the y-intercept. The coefficient is the slope, which is the steepness. That's what we're going for. And that's how we can use sliders and movable points to build an interactive, investigative tool for our students. If you'd like to continue checking out some time to play, build on your own, I've given some resources here in this activity. I will unpace and unpause it for you. And then I made a bonus slide, like what can you do after you've finished figuring out how to use movable points? Like what can we do with that activity? So here you might recall we had placed this line. I'm going to place it pretty close. When I click am I right, I'm going to actually connect this pattern and give students feedback. Nope, you missed, barely. And then when they go to change it, that line's going to disappear. So they have to click one more time, am I right? So like, let me get it wrong again. Oh, I can tell I'm wrong right off the bat. That's never going to hit it. As I move it, I've reset that timer. Now I can trace, and when I get it correct, I'll give my students a little check mark. You're good to go. Just trying to use those movable points to create an interesting interaction for them. Thanks for tuning in. I hope you enjoyed it. If you've got questions, please feel free to reach out. I hope this was useful, and I'll put that link up there again. You can access this activity, UBU ZF6, on student.desmos.com. Thanks so much.